Hi, if you're here from the LISA Symposium, thank you for tuning in. Otherwise, if you're here from a YouTube hole, then I hope you find this interesting. My name is Nimisha, and I'm a graduate student at the Centre for Gravitational Astrophysics, which is an OzGrav node at the Australian National University. Today, I'll be discussing the utility of higher order spatial modes in laser stabilization techniques, and I'll be presenting two methods currently being implemented in our team. In particular, we demonstrate a novel laser stabilization technique called tilt locking with performance near the LISA frequency stability requirement. And we also explore thermal noise reduction by a factor of 1.6 using a combination of resonant higher order spatial modes. As we know, the LISA mission will use laser interferometry to measure gravitational waves in space by taking precise measurements of distance. Laser light is a useful tool for ranging measurements because interferometric readout can be used to convert its relatively short and stable wavelength into an ultra-precise probe of strain. While lasers offer high fractional frequency stability, the required level of precision to measure gravitational waves in space demand that lasers be actively stabilized to avoid measuring stick errors. So laser stabilization techniques typically involve locking a laser to an ultra-stable frequency reference, such as an optical cavity, and then generating an error signal which can be filtered and fed back to a control loop. The current industry gold standard for laser locking is the pound rubber hole or PDH method, which involves using radio frequency phase modulation to generate an error signal. Tilt locking is another laser stabilization technique which was invented here at the ANU, where a laser is locked to an optical cavity and an error signal is instead generated by measuring the phase difference between a resonant fundamental cavity spatial mode and a higher order spatial mode, which is produced by an intentional tilt of the input beam. So this technique is an elegant approach and offers several benefits over more traditional locking techniques, such as PDH locking, like the absence of radio frequency modulation and a simplified optical path. So we've been able to demonstrate the performance of tilt locking over LISA relevant timescales. Here is an amplitude spectral density plot over the LISA bandwidth. And so the orange curve here shows the relative frequency spectral density measured between two lasers, one which was tilt locked and one which was PDH locked. And the gray curve is a measurement of the dark noise in the tilt locking system. So we've also modeled various noise sources and the LISA mission requirement, which is this green dashed curve here. So with this plot, we have shown that tilt locking is near the LISA mission frequency stability requirement and has a similar performance to PDH locking. We believe tilt locking can approach fundamental short noise and thermal limits, which makes it a potential candidate for space applications requiring high stability. So another use of higher order spatial modes is in a proposed experiment to reduce the effect of thermal noise in optical cavity mirror coatings, which is currently a limiting noise in many metrology and fundamental physics applications. For example, Earth's climate change measurements on the GRACE follow-on mission laser instrument, spectroscopy and atomic clocks, gravitational wave detection, and tests of fundamental physics like Lorentz invariance. While current strategies to mitigate thermal noise, such as cryogenic cooling and improvements to materials and manufacturing techniques, have demonstrated promising improvements, some are challenged by the demanding environment of space, where size, weight, and power requirements are carefully considered. We propose an optimized method for laser readout that offers a multiplying factor of improvement on top of current approaches to reduce thermal noise. So figure A shows just a standard setup for PDH laser locking, and figure B is a standard Gaussian beam incident on a cavity mirror, where the thermal noise is represented by the surface fluctuations on the mirror. In this proposed experiment, we would sample the cavity with a fundamental mode and several higher order modes, where the resulting readout signals are combined in digital signal processing to synthesize a flattened beam profile, such as a mesobeam beam on the cavity mirrors. This can be seen in figure C and D. By widening the effective spatial sampling within the cavity, the Brownian motion over the surface of the mirrors can be better averaged, lowering the effective thermal noise by up to a factor of 1.6 with just 3 modes. This method can be used to complement other thermal noise mitigation strategies such as cryogenic cooling and manufacturing improvements. To summarize, utilizing higher order spatial modes in laser frequency stabilization techniques, both for generating readout signals or as a way of reducing thermal noise, offers opportunities for higher stability readout and lower noise. Thanks for tuning in, and if you have any questions, feel free to reach out. Thanks.